Okay, good day. So let's have a discussion for the slip critical connections with loads passing through the center of gravity of the connections. So we have, so for a short introduction, almost all bolted connections with standard size holes are designed as the bearing type connections. So on some occasions, however, so particularly in bridges, it is felt that slipping should be prevented. So we have high-strength bolted connections may be designed such that slipping is prevented either at the service load limit state or at the strength limit state. So these are referred to as the slip critical connections. So slip critical connections should be used only when the engineer feels that slipping will adversely affect the serviceability of a structure. For such a structure, slipping may cause excessive distortion of the structure or reduction in strength or in stability. Even if the strength of the connection is adequate, so for one example, it is felt necessary to use slip critical connections when oversized holes are used, or when slots parallel to the load, direction of the force are planned. Other situations where slip critical bolts are described in section J3.8 of the commentary to the AISC specification. For the AISC specification, so the nominal slip resistance of a connection, that is the R sub n, shall be determined with this expression. So we have the R sub n is equal to mu, the D sub u multiplied by the H sub f multiplied by the T sub b, then multiplied by the N sub s. So in which we have mu is the slip mean slip coefficient. Basically, this is the same as the factor, or this is the same as the friction factor or coefficient of friction. Basically from our P6. That is 0.3 for Class A and 0.5 for Class B faying surfaces. Then we have the value of the D sub u is equal to 1.13. So this is a multiplier that gives the ratio of the mean installed pretension to be to the specified minimum pretension given in table 12.1. But we have a separate table here from our NSCP, I think. Yes, then we have the H sub f is equal to the factor of failures, so determined as follows. We have number 1, where bolts have been added to distribute the loads in the filler. So H sub f is equal to 1.0. Then number 2, where bolts have not been added to distribute the load into the filler. So for one filler between connected parts, H sub n is equal to 1.0. For 2 or more fillers between connected parts, we have 0.85. Then the value of the T sub b, this is the minimum fastener tension as given in 12.1. So again, we have our separate table for this one from our NSCP 2015. Then N sub s is the number of slip planes. Then for our reduction factors and factor of safety, so this is for standard size and short slotted holes perpendicular to the direction of the load. So LRFDN ASD. For oversized and short slotted holes parallel to the direction of the load. So LRFDN ASD. Then for long slotted holes, again, are factors for LRFDN ASD. So let's have an example for this one, the slip critical connections. So let's have our example. Determine the number of 25 mm diameter A325 slip critical bolts in standard size holes needed for the limit state of slip if the faying surface is Class A, using both LRFD and ASD method. For the steel, we have Fy is equal to 248 megapascals and F sub u is equal to 400 megapascals. So again, if we say slip critical connections, okay, so if you're using bolts as our fasteners, so we tighten this nut or nuts of this of the fasteners. For example, again, if you're using bolts, we tighten the nuts, then we put the bolt in tension. If these fasteners or if these bolts are in tension, we are maximizing the friction between these two plates. So if you are able to maximize the friction between these two plates, so we have frictional forces or frictional force that will prevent the movement of this contact area between these two plates. So that is how a slip critical connection works. Okay, so for this example, we are required to determine the number of our fasteners. So let us compute for the ultimate load, since we have a dead load and a live load. Okay, so this is our P sub U is equal to 1.2 of the dead load. Okay, the 1.2 of the P sub D plus 1.6 of the P sub L. And this is equal to, we have 1.2 of, that is 60 kilonewtons. Okay, plus we have 1.6 of 90 kilonewtons. So for our P sub U is now equal to, this is 1.2 of 60 kilonewtons plus 1.6 of 90 kilonewtons. So we have that as, this is 216 kilonewtons. Then for, this is for the LRFD. So for the ASD, this is the allowable value. We have P sub A is basically the P sub D plus the P sub L. So this is equal to 60 kilonewtons plus the 90 kilonewtons. So our allowable load, the allowable load is equal to 150 kilonewtons. Okay, so let's have the resistance of one 25 millimeter diameter bolt. So again, we are using 25 mm. So from our reference a while ago, we have the value of the R sub n is equal to, this is a mu, basically our coefficient of friction from P6, multiplied by the D sub U, multiplied by the H sub F, then the T sub B, then N sub S. So the value of mu is equal to 0.30. So 0.30, this is for class A. And a while ago, the value of our D sub U is equal to 1.13. So we are using volts. This is H sub F is 1.0. Then T sub B, this is from our NSCP. So we are using 25 mm bolt diameter. But from our table 510.3.1, we don't have 25 mm. But the nearest value is, we are starting with 24 millimeters. 1 mm is negligible from 25 mm when it comes, maybe when it comes to the strength. And we are using a 325 volts. So therefore, we are using the value of 205 kilonewtons. Okay, from our NSCP. So this is 25 mm. But again, we don't have 25 mm in our reference. We are using the equivalent value for 24 mm. That is 205 kilonewtons. Then the number of slip for this one is equal to 1. Okay, so again, from our reference, so the N sub S is the number of slip planes. So we have only one slip planes. Okay, so we are now to compute for the capacity or the required capacity per bolt. Okay, so this is the R sub n is equal to mu. The resistance of 1 bolt is 0.30 multiplied by the D sub U is equal to 1.13. Okay, the H sub F is 1. Okay, the T sub V is equal to 205. This is 205 kilonewtons. The number of slip plane is 1. Okay, the resistance of 1 volt is equal to 0.3 multiplied by 1.13. Okay, then that is 1, then multiplied by 205 kilonewtons. So we have that as 69. Okay, this is 69.4 and 95 kilonewtons. So this is the capacity, okay, or the resistance of 1 volt. That is 69.495 kilonewtons per volt. So how do we determine the number of volts? Okay, let's start with LRFD. So for LRFD, we have the design strength or the design resistance P of R sub n is equal to, so for our LRFD, the value of P is basically equal to 1.0. So this is 1.00 of 69.495 kilonewtons. So basically the same as 69.495 kilonewtons. Okay, so again, under LRFD, the required number of volts will be equal to, so from our ultimate load, the P sub U divided by the design strength per 1 volt. So again, the design strength per 1 volt is, we have that as 69.495. This is per 1 volt. So what is our P sub U? Again, a while ago, the value of the P sub U is equal to 216 kilonewtons. This is 216 kilonewtons divided by the resistance of 1 volt is 69.495, and this is equal to, we have 216 divided by that value is equal to 3.11, but obviously we don't have 3.11 volts. Okay, so for LRFD, I always round up. We are using 25 millimeter diameter bolts. So this will be the required number based on LRFD. So what about for the ASD? Okay, so for the ASD, we have the factor of safety is equal to 2.0. So we have the allowable value or the allowable resistance R sub n divided by omega is equal to, that is 69.495 to be divided by 2. So this will be the allowable resistance of 1 volt. We have 69.495 to be divided by 2. And that is equal to, is this 34? Correction. So let's go back to our reference. Is it 2.0 for ASD? Okay, so this is for the standard size. Okay, so for ASD, it's not 2.0. So correction, I will be using 1.5. So this is 69.495 divided by 1.5. So this is equal to, we have 46.33 kilonewtons. Now for ASD, how to determine the number of volts required. So the number of volts required is equal to, this is our P sub A, the allowable load to be divided by the the resistance of a 1 volt. And this is equal to, so a while ago, what is the value of P sub A? That is equal to 150 kilonewtons. So we have that as 150 kilonewtons divided by the resistance of 1 volt based on ASD, that is 46.33 kilonewtons. So 46.33, and this is equal to, okay, we have 150 to be divided by 46.33. So we have that as 3.24. Again, we don't have a 0.24 volt. So we are doing, we are to round this value up. So this is, let's say, we are using a 425 millimeter or 425 millimeters diameter bolts. So we arrive with the same value or the same required number of bolts based on LRFD and ASD. Okay, so that is based on the resistance of 1 volts, which is a slip critical bolt. But we need to consider the other factors. Okay, so after determining the required number of bolts, so let us check the bearing strength of the bolts. Okay, so this is for the total bearing strength. Okay, so how do we compute for the total bearing strength? So we have that as the R sub n is equal to, this is the 1.2 of the L sub C, then multiplied by the thickness of the plate multiplied by the F sub U. Since this is the total, we are to multiply this one to the total number of to the total number of bolts. Then it should be less than or equal to 2.4 multiplied by the diameter of the bolt, then multiplied by the plate thickness multiplied by F sub U. Again, since we are dealing with the total bearing strength, we should multiply this one to the number of bolts. Okay, from this formula, we don't have yet the value of the L sub C. So L sub C, we have from the edge to the center of the bolt, that is 45 millimeters. This will give us, let's say, L sub C number 1. Then 75 mm center to center distance. Let's say this is L sub C number 2. So since we are using the 25 millimeter diameter of the bolt, what will be the diameter of the hole? Take note that we are using, or these bolts are for standard size holes. So kindly check again what will be the required standard size on page 5-99 of our NSCP 2015. What will be the diameter of the hole for standard size holes for a 25 millimeter diameter bolt? So the diameter of the hole, for standard, basically if we have a bolt diameter, if the bolt diameter is greater than or equal to 24 mm, the diameter of the hole will be the diameter of the bolt plus 3 millimeters. But again, this is applicable if the diameter of the bolt is greater than or equal to 24 millimeters. So that will be, this is 25 plus 3. So we'll be using 28 millimeters. But for our NSCP, we don't have a 25 or 28. Okay? So kindly check that on our NSCP, we have only 27, 30, and 33. So we'll be using 28 millimeters. So what will be the value of L sub C1? Okay, L sub C1 will be equal to, that is 45 millimeters minus 1/2 of the diameter of the hole minus 28. And this is equal to, so what is 45 minus 14? That is equal to 31 millimeters. This is L sub C1. L sub C2 is equal to, That is 75 minus half, or that is minus 1 diameter of the hole. That is 75 millimeters minus 1 diameter of the hole is 28 mm. So 75 minus 28 is, that is 50. What is 75 minus 28? So I can't do it manually. I'm a little hungry right now. So we have, what is 75 minus 28 is equal to 40. This is 47 millimeters. This is again, so this is 40, that's not 45. This is 47 mm. So of course, the least value will be, we'll be using the least value, 31 millimeters. So for the total bearing strength of the 4 bolts, this is R sub n is now equal to, we have 1.2 of L sub c, that is 31 mm. Then multiplied by the plate thickness, again we are using 16 millimeters thick plate. Then F sub u is equal to 400 megapascals. Then to be multiplied by the computed number of bolts, that is we are using 4 bolts. Again, this is in newtons, so we are to divide this value by 1000 newtons. But it should be less than or equal to 2.4. The diameter of the bolts is 25 mm. Thickness of the bolt is 16. Then 400 megapascals. We are using 4 bolts, so this is to be divided by 1000 newtons. Okay, for the computed value to be in kilonewtons. So R sub n is equal to so this is, we have 1.2 multiplied by 31 mm. The thickness of the plate is 16. Okay, 400 megapascals, we are using 4 bolts. This is to be divided by 1000. So we have that as 952.32. So 952.32 kilo newtons. So is it less than or equal to this value on the right side? So we have that as 2.4. The diameter of the bolts to be used is 25 mm. This is 16 mm thick plate. 400 megapascals times 4. This is in newtons, so to be divided by 1000 to be in kilonewtons. So we have that as 1500. This is 1,536 kilo newtons. So we'll be using this value for the bearing strength. So let us check for both LRFD and ASD. So for the LRFD, we have a reduction factor for the bearing strength equal to 0.75. So we have the P of R sub n is equal to 0.75 of 952.32 kilonewtons. And this is equal to, so we have 0.75 of 932.52 is equal to 699.39 kilonewtons. Or correction, that is 952, not 932. So this is, we have 0.75 again, 0.75 multiplied by 952.32. That is 714.24. So you have the bearing strength, the design bearing strength, 714, so 714.24 kilo newtons. this is greater than the value of our P sub u. So again, the value of P sub u is equal to, that is 216 kilonewtons. So P sub u is equal to 216 kilonewtons. So this is, we can conclude that it is adequate or safe. So that is for the bearing strength when it comes to LRFD. But when it comes to the ASD, for the ASD, our factor of safety for the bearing strength is 2.00. So for the allowable value, this is, we have the R sub n divided by the factor of safety. So this is equal to 952.32 kilonewtons, divided by 2, and this is equal to, we have 952.32 to be divided by 2 is 400, that is 476.16. So 476.16 kilonewtons. Which is, again, I think this is greater than our allowable value. We have the P sub A. So this is from the actual loading. Again, our P sub A is 150 kilonewtons. So the value of P sub A is 150 kilonewtons. So again, so when it comes to ASD, using 4 volts will be safe. When it comes to the bearing strength. So after the bearing strength, let us proceed to the next factor to be considered, that is the shearing strength. For the total shearing strength, we have that as R sub n is equal to, we have F sub nb multiplied by the area of 1 volt. Since this is total, again, we are to multiply this one to the number of volts. So we have the resistance R sub n is equal to, for S, what is the value of the F sub nb? If we are using 8325 high strength bolts. So from NSCP again that is on page 5-99. The value of F sub NB is equal to 457 megapascals. For A325, F sub NB is equal to 457 megapascals. So this is 457 megapascals. Multiplied by the area of 1 volt, we are using 25 mm. So 25 squared pi, this is divided by 4, and we are using 4 volts. Again, this is in terms of the newtons, so to be divided by 1,000 newtons. So this is the nominal value, R sub n. We have 457. Multiplied by 25 squared. This is sheep pi divided by 4. Then we have 4 volts divided by 1,000. So a nominal value of 897.32. 897.32 kilonewtons. Then again, we are to check if it is adequate under LRFD and ASD. So for the LRFD, again, we have a reduction factor that is equal to 0.75. So we have the P of R sub n is equal to 0.75 of 897.32 kilonewtons. And this is equal to, so 897 times 0.75. So this is equal to 672.99 kilonewtons. Again, this is greater than our piece of U, which is only equal to 216 kilo newtons. So again, this is, okay, we can tell that if you are to use 4 volts, 25 mm in diameter, okay, the connection will be adequate, okay, when it comes to the shear strength of the bolts. Then when it comes to the ASD, so we have a factor of safety is equal to 2.00. So we have R sub n, okay, divided by the factor of safety is equal to 897.32 kilonewtons, okay, to be divided by 2. Okay, this is equal to 897.32 divided by 2 is equal to 448.66. So 448.66 kilonewtons. Okay, which is greater than the piece of A, actual loadings. So again, our piece of A a while ago is equal to 150 kilonewtons. So this is also adequate when it comes to ASD. Okay, so therefore, so it is safe, or it is adequate to use 425 millimeter diameter bolt, which sleep critical, bolts. So this will be our solution for this example.